Hey, Miss Goshorn, it's Prahan.
And Hisham.
Welcome to our Mousetrap car video analysis. This is our Mousetrap car, and today we'll be analyzing its kinematics, its forces, its energy body diagrams, its structure, and along with real-world applications. So let's get started.
Goshorn, welcome to the structure portion of our Mousetrap car video. So for the base of our car, we used just a simple cardboard base with two pieces of cardboard stuck together by tape, duct tape. For our axles, we used the insides of the pens, as you can see right here. And we used this to create a very firm base for the wheels to spin. See, I'm pushing pretty hard and nothing's happening to it. For the axles, we used wooden skewers that spin inside the pin caps. And then for our wheels, we just use simple CDs, which are lined with duct tape in order to increase friction. And this is a real-world application in that in the real world, cars and car manufacturers, they use treads on tires to increase friction on the road. We use a simple mousetrap engine, just a standard mousetrap, and we attached like four skewers to the end of the mousetrap to increase the arm and thus increase the power of the mousetrap. We also used this ribbon to attach the end of the mousetrap to our axle, and in order to get the power, we wind up the back wheels of the mousetrap. Thus, if we keep on pulling, the mousetrap, the lever will go up, and the mousetrap will spin like that.
Alright, so in addition to what Hisham said, we created this lever back here to create more distance. So usually what happens is when you have a longer lever, the mousetrap usually goes a farther distance because you're having less work per time. So because you would want to extend the mousetrap over a larger period of time to get increased distance. But if you were working with power, we'd probably have a smaller lever, so it snaps forward in a faster period of time, so thus maintaining that power over a less period of time, which would probably result in less distance but a faster speed. Other than that, we do want to mention the errors we had at first. As you can see, Hisham mentioned the pin cap axles here, and what actually happened in our first build is that the cardboard was way too weak, and so when we tried to wind it up, the cardboard apparently was too flimsy. So what would happen was the axle would just come up, and it would just get off the ground, so it wouldn't go at all. Another thing we did that on our second build that was different from our first is that we glued our wheels to the skewers. As you can see here, we glued it, and we found some toys around the house to make sure they secured in place, and on this wheel too. And what that does is instead of the axle moving the wheel, it's actually just the axle that spins and also takes the wheel with it. Other than that, we had a issue with instead of using ribbon, we used string, and that posed a problem because it would not unwind good enough, because what would actually happen is that the string would get caught up in the axle here itself, and then it would just get stuck. But in our second build, we definitely did a better job. We made sure it was double layered and made it more sturdy. And as you can see, the Mousetrap car is relatively light and aerodynamic, and what we thought was that we wanted to keep it's made out of cheap material. But what the thing is, a lot of businesses do this too in the real world, as they try to make a product with the cheapest possible, but it gets the job done. So the idea here was that it's very cheap. It's obviously built out everything around the house, but it gets the job done, and we got it to move about 6.5 meters. So this ends the structure portion of our video analysis, and now we'll move on to the written portion, computation portion. Alright, so welcome to the computation part of the analysis. So first we're going to start with kinematics. As you can see here, we have our position time, velocity time, and acceleration time graphs. So let's focus on the position time graphs for the time being. So what we analyzed was that the car sped up when the lever was getting back to its origin, we claimed the origin of the car to be the start line. So the start line was the origin, and it rapidly did increase in velocity and definitely flattened out after a period of time. So from 0 to 6 seconds, we estimated was the time that it sped up, and that was the time that the energy, the ribbon was unwinding, and then the final 1.2 seconds was it just free riding it to a stop. So we kind of said that in our description, and then we obviously assumed the start line was the origin. For our velocity time graph, this basically, we have a kind of a triangle going, but it's not exactly a perfect triangle because it did only accelerate. It definitely did only increase velocity for the first 6 seconds, and the last 1.2 seconds it rapidly decreased velocity until it hit 0. So our calculations, we wanted to calculate the VM. So as you see, we labeled here was VM, and that was the maximum velocity before it started freewheeling and before it came to a stop. So here we have our equation. It's basically the area of the triangle. So it's half T VM is equal to the change in distance. We calculated our change in distance to be 6.5 meters, and that was just from our observations when we raced the cars. So when we put it in the equation, we did all the calculations and got our velocity to be 1.81 meters per second. Also through that, we've calculated our average velocity. So the change in distance was 6.5 meters and the change in time was 7.2 meters. So we got an average velocity of about 0.9 meters per second. We assume that the car would be going at a constant increasing velocity. We know that may not be true, but for our sake, we decided to keep it at a constant increasing velocity, and we basically just described that it reaches a maximum velocity of 1.81 and then decreases to 0, and we had a 0.9 meters per second average velocity. Now moving on to the acceleration time graphs, we basically applied another equation to find acceleration. So our acceleration was actually the slope of the velocity time graph. So we basically took 2 points, so we knew that the velocity in time was 1.81 at 6 seconds and 0 at 0. So we found our acceleration 1 to be 0.302, and that actually is supposed to be at the that's actually an average acceleration of the whole thing, because that would definitely be our slope. The second portion of the graph obviously would be negative because it does go to a velocity of 0. So we took the same point at 6 seconds of 1.81 and we subtracted it from 7.2, which was 0 meters per second, and we got an average velocity of negative 1.51 meters per second. And we basically just described that here in our description. Alright, so this is just a close-up on our kinematic graphs along with our descriptions, our equations, and all our calculations. So this is just a close-up for you to get a better look.
So now we'll be talking about the free body diagrams, or the FBDs. Alright, so this is our free body diagram. The center of the diagram is our Mousetrap car. The downward arrow signifies the gravitational force, which is Fw. And since there's a gravitational force, there has to be a normal force, because the floor is pushing up on the car at the same time when the car is pushing down the floor. So Fn is our normal force. To the left, we have our friction force, which resists the motion of our Mousetrap car, and F Mousetrap is going to the right, which is the power of the Mousetrap, which causes the Mousetrap car to move. Alright, so now to the free body diagram calculations. So we calculated our gravitational force using the equation Fw equals mg, where m is the mass of the Mousetrap in kilograms, and g is the gravitational constant, which is 10 meters per second squared. So we did these calculations, and we found that the gravitational force was 2 newtons. And since the gravitational force is 2 newtons, we know that the normal force also must be 2 newtons. And this is because the Mousetrap car stays at a constant height, which is 0 meters, And since there's no movement vertically, we know that these two forces, normal and gravitational, are both the same. And also, we calculated our net force in relation to Newton's second law. And the Newton's second law states that F equals ma, where F is the net force, m is the mass, and a is the acceleration. So the mass was 0.2 kilograms, and our acceleration, and this acceleration is at 6 seconds, which is the maximum acceleration, is 0.302. And when we did this calculation, we found that the net force is 0.0604 newtons. And this is the net force that is causing the car to accelerate. And now on to momentum and impulse. So our momentum calculations. The equation for momentum is P equals mv, where m is mass in kilograms and v is the velocity of the car. And this equation right here, P equals mv, is for a mass moving with velocity, which is our car. So our mass was 0.2 kilograms, and this velocity, which is at 6 seconds, is 1.81 seconds. 1.81 meters per second. And so when we did this calculation, we found that our momentum is 0.362 newtons. Okay. And impulse. Impulse is defined as the change in momentum. And since we were calculating the impulse from t, when time is 0, to time is 6. Since the momentum at t equals 0 is 0 newtons, and the momentum at t equals 6, which is what we calculated here, is 0.362 newtons, all we need to do is subtract these two values, and we can find what our impulse is. And so this equation shows the relationship between impulse and momentum, because impulse equals change in momentum. Thus, we're just subtracting the momentum at time equals 6 minus the momentum at time equals 0, and then by doing this we find out that the impulse was actually the same as momentum, which is 0.36 kilograms meters per second.
Alright, so welcome to our energy diagrams portion of the video. We'll just be analyzing the energy diagrams and the change in energies throughout the system. Okay, so initially the car does start with no energy at all. It's actually 0. So what actually is when it's not wound up or anything, and the car is not in motion, there's no force acting on it, so the energy level is 0. But when we do start winding up the car, we're putting in work into the system to create potential elastic energy. So this work would actually equal the potential elastic energy. And so we cannot calculate this work because we do not know the spring constant in this situation, but we do know, like I said, that work that we put in would equal the potential elastic energy. And this potential elastic energy does represent when the car is fully wound up and is ready to go into motion. Continue on. The potential elastic energy, when we release the car, it converts from potential elastic to full-on kinetic. And actually, the full-on kinetic energy is only reached at the maximum level before it starts free riding. So this represents that velocity maximum. So this is why the velocity maximum was so crucial, because it was relevant to every calculation we kind of made. So, and after the kinetic energy is reached, it does free ride because there's no more energy to provide to the system to make it keep on going. So from there, friction is just what acting against the system to slow it down, and eventually we reach a energy level of 0 once again. We don't have potential gravitational because we are on a flat surface, so we know that the reference points for potential energy is at 0 meters or where we're putting the car into motion. So the track would actually be the reference line. So we know there's no potential gravitational. The only potential energy that we have is the elastic energy. And here we just did a calculation because we know that the kinetic, full-on kinetic, minus work 2, and here work 2 would represent our friction force that it's acting against the system. So here we know that the kinetic energy minus the work 2 would equal 0, because we know at the end it would result in a energy level of 0. So we know that KE would equal work 2. We know that the kinetic energy equation has half mv squared, and we know it would equal work 2. In this situation, we don't really need to write out the equation for work 2 because that's what we're trying to solve for. So half 0.2, which was our mass in kilograms, times the velocity at the maximum point, which is 1.81, and we square that number to equal work 2, and you end up with an answer of 0.328 joules of work. And this work obviously would equal the kinetic energy at the maximum level. Thank you for watching this, Goshorn. This concludes our video analysis. I hope you liked it, and thank you. Thank you for your time, Mrs. Goshorn.